My name is Drew Kirkman with Hubbard Radio in Cincinnati, and I am a member of the program committee for this year's conference. I'm here to introduce this session, focusing on directional FM antenna modeling and some AI-based innovations that have been developed to help broadcasters transition from physical modeling to more efficient and accurate computer-simulated modeling. And we're pleased to have Dave Benco from Dielectric here to present the session. Dave is Dielectric's national sales manager for the western half of the United States. He has more than 25 years of experience in terrestrial broadcasting, having previously worked at Electronics Research, ERI, Gates Air, Roda and Schwarz, and Axera. Am I getting that right? Okay. Dave is a member of the Association of Federal Communications Consulting Engineers, the IEEE, and has been a featured speaker at numerous technical conferences. Dave, thank you so much for being here this morning.
Thank you. All right, so I bet you thought you might have a chance to not see a presentation including the letters AI during this conference, but if you haven't seen one already, well, I hate to break it to you, but we're going to talk about AI a little bit today and how it helps us to make better FM antennas and filters for the industry. So what I'm going to talk about today, we're going to talk about how we use AI optimization to develop FM directional patterns. So I'll cover a little bit of the history as well as some recent changes at the FCC in terms of rulemaking that paved the way for this technology to be used by manufacturers and broadcasters to qualify patterns for FM directionals. And even a little bit of bonus content today, I'll talk a little bit about using drones to verify those measurements in the field. That seems to be a hot topic that we discuss often with our customers as well. Second, we've got some AI type applications that we use when we're designing FM combiners. So when you're designing a combiner, you sort of have to plan for all the different frequencies that are in there, and the line lengths and segment lengths get to be very important, right, when you do that. So what order are the filters in? And we'll talk about how AI helps us to design combiners that allow flexibility for future expansion or and improve the power characteristics. Therefore, you can do more power, right, to the antenna and less power into the load. So we'll talk about how we leverage those computer tools there as well. All right, this slide I stole from John Shadler, our VP of Engineering. I love his sense of humor. He says, we're really talking about bringing FM into modern times. And on the left there, you'll see a photograph from, when you talk about dinosaurs, you talk about these different eras, right? This is the Palmyra era of test ranges. This is the range that existed in Palmyra that Dielectric purchased, and now you don't need to use a range like that anymore. It was a full size, full scale range. You can use these computer tools now to do the same job, right? So we'll talk about what it takes to get from there to here. Also, when you're building the models, if you've ever seen that done where you're building a model of an antenna, whether it's a full-size model or a scale model, there's a lot of bits and pieces that go into that, and it's kind of an arts and crafts project. So that's what this sort of is to represent here in the bottom center of this slide. But basically, and you see in the bottom right the animation there, as you manipulate those elements, it changes the pattern that comes off of the antenna, obviously. So you want to know exactly where to place those to best hit your target pattern. And that's what the computer tools help us to do. So ranges used to look like this. This is a picture of on the left, the Gibbsboro, New Jersey test range that RCA and then later Dielectric had in operation for verifying patterns both on TV and FM antennas. So you can see it's not insignificant in the amount of just physical space that it takes, right? The reason for that is you've got to make sure you're doing far field measurements, right? If you want them to be accurate, you've got to get far enough away from the elevation pattern specifically to get a good far field measurement. There's a picture there, the Palmyra picture that was on the previous slide as well. And you'll notice here the antenna is horizontal. No, we don't install them that way. We turn them up, but we do test them that way. So it is a little bit easier to have someone move along horizontally than it is to move vertically. So this is sort of how it used to be done, and then somewhere later we developed the ability to do this type of testing indoors in an anechoic chamber. In fact, this chamber that you see pictured here, this 60-foot tapered anechoic chamber, when it was built, was the largest chamber in the country back then. That since has been dismantled. We don't even have that at Dielectric anymore. It's actually at the University of Maine. They use it for some testing there that they do. But we also had a 100-foot cylindrical range in Raymond, Maine as well. And there's a picture on the right there of what the inside of an anechoic chamber looks like. Have you ever been inside an anechoic chamber before? It's a little bit creepy, isn't it, when you go in, like the way the sound deadens, and it does the same thing for RF, right? So it's designed that you're not measuring reflections in there, just like in the real world, right? So the first thing you need to do when you're trying to do a study is you've got to find materials to make a model. And in practice, this is kind of how it happens. There's a container out back that has a bunch of tower sections in it that match whatever the customer has. We like to get good data from customers about their tower and what's on it, right? Sometimes that's more difficult than others, right? You say, hey, I need, this is a discussion I had with a customer not long ago when we were developing an FM directional for them. I said, I need to get tower data. He said, oh, it's a stainless G7 tower. You should have that. I said, okay, what else is in the aperture of the antenna? He said, oh, there's nothing else there except, well, there's one 6-inch line that goes up through there, but that's it. And I said, okay, that's fine. So there's nothing on this face. Well, on that face, I mean, that's where the ladder is, but, does that matter? Yes, the ladder matters. We need to know about that too. And I said, well, how about on the other face? He said, well, there's another line over there, but I don't think it'll really be in the way because it's behind the elevator shaft. And I said, okay, this is starting to get more complicated than it sounded at first, right? This is a constant battle that you have when you're doing these models, right? The chances are that someone's going to go onto the shelf at the factory and find exactly what you have are 0. So they're going to have to find something that's very close, and they're going to have to modify that to make it match exactly what you have. And that's what guys like us do and have done for years when we're building models. So we finally built a model of the tower, and we get all the data that we can, and we model that, whether full size or at scale. And then we add an antenna bay, right, a radiating element to that. And we're trying to achieve a pattern, right? So the good news is we've got some experience at this, right? So we don't have to start from 0. We kind of have an idea of where that thing should go on the tower and what orientation it should be and how far off it's going to be and maybe how many different parasitic elements will be needed to make that pattern, but you don't know until you build it and start taking some test data. So the process of building it is you put a radiating element up there, you start adding some metal rods, you zip tie them in place, you affix them as, at whatever angle you think is going to be best for the first pass. There's lots of metal tape involved in this process. I mean, it really is sort of an art here to build that test fixture, and then it goes either into the chamber or onto the range for data collection. So this is not a fast process, as you can imagine, right? So it takes time to gather the data, it takes time to build the model, and then it takes time to take the data in real life, right? You've got to take that data, you've got to analyze that data, and then what you're going to do is go back to the model and make some changes to see if you can improve what you just did, right? Well, back in June of 2021, Dielectric, in conjunction with some help from a consultant named Merrill Weiss, filed a PRM. Anybody know what PRM stands for? This is your FCC acronym quiz. Proposed rulemaking, that's right. So we said, we think that this should be a rule, right, to the FCC. We think it should be a rule that you would allow computer simulation to be substituted for range simulation for FM directionals, right? So then in November of 2021, so 5 months later, the FCC decided to move forward with an NPRM. Anybody know what an NPRM is?
Notice thereof.
Right, a notice of a proposed rulemaking. So this is when the PRM goes to the FCC. This is something that a petitioner, like Dielectric in this case, goes to the FCC and says, hey, I think it would be great if you made a rule like this. And then the FCC turns around and tells the public, look, we're considering making a rule like this. That's the NPRM, right? So what happens when there's an NPRM is they listen for, hey, what does everybody think? We're thinking of making this rule. What do you all think? Well, there's a comment period that in this case, because there was strong support for the PRM, this comment period was only 30 days, but there were 19 commenters who responded. 18 were positive, 1 was opposed. So the support from the broadcast community was strong. This is manufacturers, this is broadcasters, this is anyone interested in commenting is allowed to do that here. So in May of 2022, the FCC did adopt this rule change. And the actual text from the ruling says that to verify a particular antenna model for simulation, the broadcast station must submit to the commission both the results of the computer modeling and the measurements of either a full-size or scale model of the antenna demonstrating a reasonable correlation. So it said, look, if you want to offer this antenna model, you've got to, for the first one, you've got to show us that that model, the range results and the computer results demonstrate reasonable correlation, right? Anybody in here know what reasonable correlation means? Who's the most reasonable person in here? Anybody married in here? You know what being reasonable is? So, this is a little bit fuzzy, right? So Dielectric sort of took the lead here, and we submitted the first antenna into this process, okay? And in so doing, we said, look, we're going to take a shot at what we think it means to have reasonable correlation, okay? We sort of defined the template here for what that means. We said we think that this quantity called a figure of merit should be determined by the correlation coefficient. And if you guys are like me, you loved stats class in college, right? I mean, you just love talking about how many ways you can roll dice and choose marbles out of a bag and all of that stuff, right? There's this thing called a correlation coefficient. Basically says if you compare two data sets, how close to being the same are they? If they're exactly the same, that correlation coefficient is 1.00, right? If they're not very close, it's 0.001, right? So we proposed that this correlation coefficient, when you compare those two sets of data, if that correlation coefficient is 95% or greater, that would demonstrate reasonable correlation, okay? So we took a stab at defining that. And the FCC actually liked that model, and they said, okay, we approve your petition to be able to offer that model with computer simulated patterns. So you'll see here the two azimuth patterns that I have up there show both the H pole and the V pole. And just to give you an idea of what 95% correlation looks like, that's what you see there. So you see the blue curve is the simulation that comes out of the computer. The red curve is what you see that comes off of the range. Now, why do you think the computer curve is nice and smooth and the one off the range isn't so smooth? Well, off of the range, it's the real world, right? You've got reflections, you've got maybe dimensional errors, right, in the actual building of this apparatus, right? You've got test equipment that's not perfect. So that 95% only needs to be 95% because, not because the software isn't good enough to give you a good answer, it's because the range can only be so good, right? The test equipment you're using can only be so good. So it wouldn't be fair to say they've got to be 100% correlated is my point, right? Because no range can do that. So now we're ready. We've got this process in place. And some of the steps are still the same, right? So you still need to choose a model that you're going to use. Now we're choosing them, though, from a library of files, not from a container out back that's got different tower models in it, right? We choose those library, from that library, a different tower section. We add different features, right? Like my customer's elevator shaft and his transmission lines and lighting conduits and climbing ladders and all those different features of the structure. And then we add a radiating element in what we think is a good orientation, right? Except now, instead of taking some test equipment and going to the field and taking data and recording that data and manually processing it, we let the computer do that. We let the computer do that, and it actually can move that bay around the tower, find the best place to start from, right? It can actually add different parasitic elements and move them in relation to the radiating element and the tower, so we can move that. We can increase the standoff. We can go from 11 inches to 16 inches. We can come back into 14 inches, right? Hey, remember when you were a kid and your parents were watching the game and it started to get kind of out of whack and you had to go behind the TV and they said, well, hold it up over here, Anybody that old in here? Yeah, and you get to the point where you can't move anymore, right? Because they're moving you back and forth. That wasn't AI, that was NI. That's natural intelligence right there that's going on, right? But it's the same idea, right? You say, hey, can you move this a little bit? Doing that in real, in a real model is very tedious. Doing it in the computer, you just let it run overnight, come back in the next day and see what you came up with. So, adding those parasitics to shape the patterns, then we check, make sure, okay, does it still comply with the protect envelope that the consulting engineer gave us, right? We're not stepping somewhere we shouldn't step. And then are we hitting the coverage targets that the customer has, right? Oftentimes this process results in something that we think is a great solution, right? Hey, this covered up a lot of that area that you wanted to cover, and they go, yeah, but the worst part is right over the best part of my population. Can you tweak it a little bit to be better over here, and I don't care so much about this? And then we go through and do it again, right? When you're doing that on a range, it takes time, days, weeks to get that done. When you do it in the computer, much, much faster. So this whole process we've replaced with something called artificial intelligence optimization. And you might think, wow, that sounds really fancy, right? I bet it's expensive. Okay, well, yes, it is, but it's a one-time cost, right? So the upfront cost is expensive because you've got to buy the tools, you've got to train the people, but after that, every project that you do is where you see the benefits. So we use a type of optimizer that's called particle swarm optimization theory. So we use that, and honeybees also use this theory, okay? They have it programmed into their firmware, right? We have to buy software to be able to do it, but the way it works is you define what a good solution looks like, right? Then the software computes what the solution is with the hardware arranged as you have it, and then it changes something and sees, does that dot move closer or further away from a good solution? And then it does it again, and then it does it again, and it does it again. And it keeps doing that until you reach the target, right? In this case, we'll define, maybe you say, I need to be within the FCC protect contour. I've got to cover, 85% of this area. My H-pole, by the way, has to be greater than my V-pole ERP in every direction. My H-pole and V-pole, they should track together, right? I wouldn't want to make a change where all of a sudden I've got a lot of V-pole energy over here and a lot of H-pole over here, right? And you have to put some practical limits on it as well. In other words, the number of parasitic elements that you use. You can't have 100 different parasitic elements here, right? You want to try to keep that down to a couple of parasitic elements, right? It gets really complicated. Where are they? Sometimes the software will tell you, well, you want a great pattern, all you have to do is be on a standoff 48 feet away from the tower, and it looks really nice and smooth, right? Well, not practical, right? So we put some limits on where the radiating element can go, and what the positions are, just in terms of manufacturability. But the result of that is, once we do that, I tried to capture it all on one slide here, but I thought it's kind of small. So the next few slides I'll zoom in on these to show you. But This is an example. This is a C-Bay antenna, DCRC, on a 6.5 foot tower. So you can see our starting point here. This is what it looks like when we said, okay, what if we start here? We'll put it on this leg of the tower, and the green contour that you see, that's the FCC Protect contour. In the top graph, you see the H-pole and the V-pole, and in the bottom, you see the composite, right? So if you stopped here, you would fail the first test, which is the FCC Protect doesn't meet that, right? So this is where we start, and we let the computer run from here until it gets to this point, right? Now here you see that the H-pole and V-pole in the top graph are correlated. They're, sort of in the same direction there, and we get good coverage of the FCC Protect there in the bottom, right? So how do you get between here and there? Also, you'll notice on the left, you can see the parasitic elements there in orange that have been applied to achieve that type of performance, okay? The progression as it goes through and the software moves the antenna around, right? Imagine doing this on a test range. This particular antenna took 320 iterations to get from start to finish. I'm showing you here every 10 iterations, right? So there's 32 steps in this little animation here. But as the iterations go forward, you see the pattern gets better and better and better, and the swarm of bees starts to converge at where the pollen is, right? So this is one of the graphs that we use for that. This one shows the length of the left parasitic versus the angle of the bay, and then what the output coverage is, right? And you have a graph like that for, as you see on the right-hand side, for multiple different parameters. All those parameters that you can change, each one has its own swarm that happens, right? After 320 iterations, it took, I think, about 20 hours for the computer to run through these and determine the best solution. Imagine doing that on a range, right? You're not going to get 320 shots at it, right? You're going to do several, right? But it's not going to be 320. You might get an answer that achieves some minimum level of compliance with your starting parameters, but it won't be the best level, right? We probably could have stopped, hundreds of iterations sooner and still not violated the FCC Protect contour, right? We could have stopped and not had maximum coverage in every direction before we got to 320. Now, after that, it will continue to get better, but the returns diminish after that, right? So you get to a point where you go, okay, this is about how long it's going to take. More complicated, if you put more parasites in there, maybe it can get better. Takes longer to run, right? So that's why we limit that in hardware. So how do we apply this approach when we're doing this? Well, we don't use it just for FM pattern design, right? That's a nice, very clear way to explain and to show that technology, but we also use it to design a lot of products at Dielectric, right? And, when we do prototypes, we don't build them out of metal anymore. We build them in the computer, right, to see first how they're going to perform. Saves time, saves cost, makes changes a lot easier, right? Oh, delete that. Okay, great. You don't need to send to the machine shop some instruction. You can just say, let's move that probe an inch to the right and see what happens, right? Much easier to do. We've designed patterns for TV antennas during repack. We've done hundreds of them here. We've validated some older models as well, right? Now here's where I said I'm going to give you some bonus content. I wanted to include these just to show how the HFSS result and the drone measurement in the real world, how they correlate with each other. So you can see here, I can't, well, the red is the simulation and the blue is the drone measurement, right? So you can tell that they are highly correlated. By the way, during repack, we did a couple of these, and we did find out that sometimes, an antenna can be installed one bolt hole off, right? You can see it on this, right? It's pretty obvious. Patterns like this, where you think, okay, this is what I should be getting. Is that what I'm getting, right? patterns. It also works in the elevation pattern, not only in the azimuth, but you can do elevation. And this is where it's particularly interesting because getting into the far field on elevation is tough if you're doing a drone, right? If you're flying a drone, you've got to be, a half a mile or more away to get into far field on your elevation pattern. So typically when the drone is flying that circle within 400 feet of your structure, you don't need to have an FAA waiver to do that, okay? So it would be really nice if you could take all the data within that 400 feet. Well, if you do that, you're going to get near field data for the elevation pattern. Well, the good news is because of the software, we have that in the software. So we can take your measured near field data and look at our software predicted near field data and see that they match, and then you can be confident that your far field data is going to be good. So that's what these three graphs show. The top one is the measured data at far field versus the software simulation. In the middle there, you see the software simulation for the far field versus the near field, right? I think blue is the far field and red is the near field. And then finally, the drone versus what's predicted by the software. So you can see the data lines up there, and the idea is proven, and it works for various different drone measurements that we've taken. So I wanted to include some of that just so you can see another benefit of using computers to do this modeling. If you did the modeling on the range, you would have to measure the near field data and then measure the far field data, right? But if you built the antenna and didn't measure that when it was being built, well, you'd never have a chance to do that again, right? You'd never have a set of, quote, factory data. Here, if we've got the model built in our software, we could do the factory data after the antenna's been installed, right? Okay, so what it does is it allows us to compare the two methods, a range method versus AIO method. Well, with a range, even if you do a scale model to make it smaller and easier to manipulate, make that arts and crafts project a little bit simpler, right? It still takes you about 4 hours just to set everything up in the right spot on the tower model. Now you're going to adjust for the pattern. That takes 20 minutes, and it's going to be on the range for a week so you can test it and tweak it. And so your lead time's about 5 days there. You got to do, let's say you do 120 different iterations. That's going to take you about 40 man-hours to do. You could do the same thing in software in about 1 man-hour. Now, it's 1 man-hour, but it does take the computer about 20 or 30 hours. But you do the first one on Monday and you let it run while you set up the next one to run. It's going to run on Tuesday, and your engineer, the key resource, is only consumed for 1 hour per project in this case. So a huge difference in terms of simulation time and the number of iterations that you can run. So you get a better solution at the end as well. So not only are there the cost advantage, but there's also an advantage here in that once we've run that simulation and you're ready to manufacture that antenna, we've got exact dimensions on what everything should be, right? That can go straight into our manufacturing drawing process. This is exactly where it should be. This is exactly the angle that it should be. And it's completely reproducible. We could do the exact same thing again. Another area that we use software is for combiners, right? So in a manifold combiner, I'm thinking for FM here, you've got the key piece is this spline that goes along, right, and picks up all of the different stations and puts them into the mix. And the length of every one of those links is critical, right, when you're doing this type of design. They're typically not very flexible, right? If you need to add another channel or change the bouquet of channels that are in your manifold combiner, you typically need to replace the spline of the combiner, and it's a time-intensive and expensive process to do. So I'm going to walk through really quick what a mechanical or what a manifold combiner is versus a constant impedance combiner, and then how we might analyze a market to see, okay, what's the real practical benefit here? So, and I've got, 5 minutes till lunch here, right? Okay, so we'll really work up an appetite in these last few slides. All right, the manifold combiner package is basically one filter element per station here, right? So you've got, in this case, you'll see, a 7-channel configuration for FM. We can do this and put all of the outputs at the exact same location, right? So you can, I think did my animation run there? No, it didn't work. So, you can move the filters in and out if there's a problem, right? You can exchange them. And the footprint here versus a constant impedance design where you've got 2 filter elements per channel is much, much smaller. So you'll see here, for example, the 378.4 square feet requirement for a constant impedance filter. If you do it in a manifold, it's about 170 square feet of floor space. So much smaller footprint here for the manifold design. And, I said I love statistics, which was a lie earlier in this presentation, but here's another formula from statistics that basically says if you can have a fewer number of parts in your design, the reliability will be better, right? Every part has a chance of failing. The fewer parts that you have, the lesser chance you have for something to fail. So, the reliability of a filter, the requirements are very high, right? People don't want their filters to fail. It's not an active component, right? So it's expected that filter is just going to sit there and perform year after year. So we want to reduce the number of parts in there as best we can, and the manifold allows us to do that and make it more simple. Also, in terms of stability here, the inputs and the outputs remain stationary when you're adding channels. So you only need to manipulate the filter that's changing, right? What you do is you'd remove these U-links and replace them with pre-selected lengths that the computer is designed to tell you, okay, if you've got this channel in the mix, you need this length here and this length here, and it puts that plan in place for you before you ever go into the field to do that. So, for example, if you've got, you can design a 7-channel combiner. You can only put those first 5 in there right now, but you can have the appropriate U-links ready for when you want to add those other channels. And it'll tell you here even what the range of possibilities are for those other channels. For example, you've got, okay, maybe you want to have a spare filter on hand in case something happens, right? Maybe you want to, you're sharing a site and you think, well, that guy would love to move into my shared antenna, but he can't do it until next year. Well, great, you can build that with a space for him there that's ready. We'll give you a short that goes in there until he's ready to move in, and then when the time comes, he slides his filter in, you change a couple of U-links, and you're on the air with the combined system. The unused ports, like I mentioned, are capped with electrical shorts, and all that output spline, all those different configurations, all get done in HFSS, right? The shorts are based on that specific frequency, right? So, this spot, here's the short that goes in there. When you remove that short, you replace it with the filter on that specific frequency. So electrically, it looks the same, right? So you think, well, how does HFSS help you? I mean, there could be, thousands of different combinations and permutations here, right? Well, first, the data that goes into HFSS basically is the S parameters of the filter. So we characterize those filters in HFSS, and then what we do is, based on how many you want to put in this arrangement, we can have HFSS and AIO determine, okay, what's the most efficient way to arrange those that uses the smallest number of different U-links, right, to achieve that performance. And the result is, well, you've got a spline that's now been defined. So you can start out with 5 of the 7, and then you can add 1 more to go to 6 of the 7 are filled, and you change the blue links there. And then when you go to all 7 are there, you change the links to the red ones, and some of those may be the same. You just move it from here to there, right? And you don't have to start from scratch every time, right? When you look at a manifold combiner versus a constant impedance combiner, for the manifold, all the positions electrically are equal to each other, right? The loss is very similar because the filter elements are similar. The reflection is similar. Group delay is similar. Every station can achieve a 1.06 or better, regardless of whether it's the first one in line or the last one in line. The voltage here is going to be limited by the filters, not by the hybrids like it will be in a constant impedance design, especially if you get up over 4 or 5 channels. Those last couple of hybrids really handle a lot of power. So for the constant impedance, the further away you get from the antenna, the more loss you've got to incur, right? Because you're going and you're bouncing off of everybody else's filter, right? So if you look at these tables, you can see for station number 5, we're looking at 0.71 dB of loss, which takes your efficiency from 89% down to 85. With the manifold, everybody's around 90, right, or better. So, you get better performance there. If you look market to market and you think, well, practically, how can all this work? Well, okay, let's look at a market. You've got to have, let's pick a specific market, like in Boston. There's 21 stations there that could potentially move into a common antenna. And if you take out the LP and the directional patterns, and let's just say we're only going to look at the omnis, right? Because remember, the other factor here is everybody's got to share the same antenna, right? So you got to have similar patterns to start. So there's 9 stations here that could possibly join in here. What if we say, okay, let's pick a 7-channel solution that, we've got 5 of those guys that want to move in now. We're going to build for 7 of them that want to come in. And we can run all of the different combinations and permutations of, okay, you're going to start with these 5 and plan for 2 of those other 4 to one day move in, right? What does that hybrid or manifold combiner spine look like? Let the computer run the solution. In this case, there's 6 possible solutions for this market, so that makes it a little simpler. We can run those 6, and we can be prepared to offer those 6 to you right out of the gate. Same thing if we analyze another market like St. Louis, for example. This is true all across the country, by the way. If you do this kind of analysis, it becomes quite manageable with the software tools that we have. Conclusion is, historically we've used CIF combiners, constant impedance filter type combiners for these systems to expand because, it's a broadband port, right? You can put anything in there. But the manifold is a viable alternative if you can plan ahead to have it ready using the tools in HFSS based on, hey, this is the guy who could move here, right? You can get a smaller footprint, fewer parts means better reliability, and it's basically a more economical solution to solve the same problem, right? Computers are great when they make our life better, right? But it is a different skill set. It is a different competency, and through Repack, we use this tool extensively. We've gotten very proficient at using the tool, and we're now applying it to FM as well as TV, so we can take advantage of some of those things. And it's great to see, that type of innovation in the FM space as well. So I think I've got 30 seconds that I used up about a minute ago, but I'm going to see if somebody has a question here before we wrap up and go get something to eat. Anybody have a question, comment? Best presentation you've seen all week, right? I'll take any of those. Stop by my booth and see me later if you have any questions. Thank you all for your time. I appreciate it.